Hello everyone, so this is going to be a GCSE Combined Science Trilogy past paper walkthrough for Physics Paper 1 higher tier. And this was the paper that was sat in June 22. So I'm going to model it, go through how I would have tackled it, and you've got the links to the paper and Markscheme in the description. So question number 1 then. Figure 1 shows some of the energy resources used to meet the demand for electrical power in the UK on one day in 2020. So you've got this graph here, you've got the demand for electricity in the UK, and you've got the sources of energy used to meet that demand. So gas, nuclear, wind, coal. Question number 1, the maximum demand for electrical power on that day was 6 p.m. Determine the percentage of the maximum demand for electrical power that was met using generated using gas. So if I go back to the graph, I've been told the peak was at 6 p.m. What percentage of the electrical power came from gas? Well, if I go to the graph, I can see my demand for power at 6 p.m. on my graph is 30,000. Okay, and I can see my gas. If I work out what my gas peak was at that same time, you've got 15,000, you've got a gap of 5,000, okay, divided by 10 squares, so therefore each little square is worth 500, 15,000, 15,500, 16,000, 16,500 would be your gas. So you know it's 16,500, which is your gas, over your total demand, which was 30,000. So 16,000 over 30,000, this is the percentage, times it by 100, and that would give me a total of 55%. The UK government wants to reduce carbon emissions as much as possible. Which of the energy resources need to be used less to achieve this? Well, first option here, coal and gas. Both of them are fossil fuels, and therefore that would be reducing CO2. Nuclear doesn't produce any CO2, so it's not that. And wind is renewable, so that doesn't make any CO2. So therefore, it must be the top one. Question 1.3. A network of transformers and transmission cables transfers electrical power from power stations to consumers. What is this network called? Well, the whole network is called the national grid. So the whole circuit between power stations, the pylons, transformers to our homes is called the national grid. Has to be that word exactly. Explain how using step-up transformers make the network more efficient. So we should remember, after our power station, it then goes to a step-up transformer, which then pushes the current along the pylons to our homes, where it has a step-down transformer and then connects to our homes. Okay, so that's the rough cycle of the national grid. But why do we use step-up transformers in the national grid? Well, step-up transformers, what do they actually do? They increase the potential difference in the circuit. So as they increase the potential difference in the circuit, that makes the electrons basically shoot really fast down all the miles of cable to our homes. So that's the first thing that happens. So the potential difference is increased. But they also decrease the current. So it doesn't send loads of electrons at once. It sends a few electrons at a time, but really, really fast along the cable. So it also decreases the current, and this reduces heat loss in the wires. You would know if you've done a practical with a wire and you've put the current up really high, you see the wire gets really hot, which loses loads of energy. Step-up transformers do the opposite. So you know they increase the potential difference 1 mark, they decrease the current 1 mark. And that reduces the heat loss in the wires to the surroundings, which would be your final mark. So obviously as we're driving along the countryside, we see loads of cables, but they're not glowing hot, they're not losing loads of energy, they are perfectly cool because the current is really, really low. Okay, that's question. Okay, question number 2 then. A student made measurements to determine the specific heat capacity of vegetable oil. Figure 2 shows the equipment used. You've got an electric heater, a joule meter, a beaker, a top pan balance and a thermometer. Describe how the student could use the experiment shown in figure 2 to determine the specific heat capacity of vegetable oil. So you probably in school did your specific heat capacity required practical with a metal block. However, they want you to do it with oil, but it's the same principle. You should remember specific heat capacity, the definition of it is the amount of energy, is the energy needed to raise 1 kilogram of a material by 1 degree Celsius. The equation that you'd get given on your equation sheet is energy equals mass times by specific heat capacity times by temperature change. But you want to rearrange that equation to find your specific heat capacity. So specific heat capacity equals energy over mass times temperature change. So basically we need to find out how much energy is used in joules, the mass in kilograms and the temperature in degrees Celsius to then work out the specific heat capacity of the oil. And you've got the equipment here that you need to use. So point number 1 then, what I would be doing is getting my beaker and I would be putting it on my top pan balance and I would be recording the mass of oil that I've got. Now I would try and keep it at 1 kilogram because that's my definition and that just makes the equation just a little bit easier. So I would put beaker on top pan balance, use the words that they've given you in the question. You would then measure 1 kilogram of oil using the balance. So that gives you your mass, which is one part of your equation. You've then got to know the temperature change. So what I would then do is put the oil on the heater and record the starting temperature. Okay, so record the starting temperature of the oil. You would then use your electric heater to heat the oil. Sorry, I missed off one thing. Recording the starting temp using the thermometer. Try and make sure you record and use every piece of equipment they give you. You then heat the oil using the heater for a length of time. Doesn't matter how long, but normally about 10 minutes is a good range to do. So heat the oil using the heater for 10 minutes. Okay, then after you've heated it for 10 minutes, you are going to record the joule meter reading, so the amount of energy that's gone into the heater, and the new temperature of your oil. So record joules of energy used by the heater and the final temperature of the oil. What you would then do after you've got that, okay, is calculate your temperature change. So all I would be then doing is doing our final temperature minus our initial temperature. And then what I can then do is substitute the values into the equation. So specific heat capacity would be equal to your energy from your joule meter divided by your mass, which would be 1 kilogram, times by your temperature change, which you've just done, and that would give you your answer. Now, setting it out like that, this is probably the hardest required practical in physics paper 1, but yeah, that's how you need to kind of set it out, say how you use the equipment and how it links to that question. Question 2.2 then, give one risk of using the equipment in figure 2. So you've got an electric heater. What is the risk of using a heater? Is simply burns. Okay, it could burn you, it could scald you. That is the key thing. You could also say a risk would be from the glass cuts from glass. But you don't have, say, the actual hazard. Okay, the hazard is the object. The risk is what can actually happen to you from it. A different student did not have a joule meter and calculated energy transferred by the heater. So this is probably what you guys did in your required practical, because joule meters are very expensive. Use the physics equation sheet to help you answer the next two questions. 2.3 and 2.4. Write down the equation that links energy transferred, power and time. If you look at your equation sheet, you will see power is energy over energy transferred over time. That's what would be given to you. The electric heater had a power output of 50 watts. Calculate the time taken for a heating element to transfer 4,750 joules of energy to the vegetable oil. So I need to rearrange this equation. Power is energy over time to make time the subject of the equation. So if I rearrange that, time would be equal to energy divided by your power. My energy is 4,750, my power is 50, which gives me a time taken of 95 seconds. In a deep fryer, vegetable oil is heated by an electric heating element. Food is then cooked in the hot vegetable oil. The deep fryer contains an electrical component to monitor the temperature of the vegetable oil. Figure 3 shows the resistance of this electrical component and how it changes. So you've got increasing temperature and decreasing resistance in ohms. What is the electrical component used to monitor the temperature of a vegetable oil? Well, there's only one electrical component that you've looked at that basically changes resistance in response to temperature, and that is a thermistor. So thermistor is just your resistor with your flat line and then our diagonal line going through it. It's asking for the name of it, so it's just thermistor. Question 2.6. The electric heating element in the deep fryer automatically switches off when the vegetable oil reaches a certain temperature. Figure 4 shows how the temperature of the vegetable oil changed after the deep fryer was switched on. Determine the resistance of the electrical component when the electrical heating element automatically switched off, using figure 3 and figure 4. So in this question, we can see that we're told that it automatically switches off at a certain temperature in this graph here, but we need to get the resistance from it at that temperature. So what I would do is identify when our heater would be switching off, which would be the point where the line would then go flat, which would be this point here. And if I read that down, that should give me a reading of 3.4 minutes, and reading it across at the temperature would give me a reading of, if each little square is 160 degrees. Now it's the 160 part that I'm actually interested in, because then I can take that forward to my graph over here. I go to 160, I go along, and I can then work out what that value would be. Well, you guys would do it much more accurately than me, just on an iPad, but if you drew it really accurately, it should give you an answer of 250 degrees Celsius. They would accept, though, any range of between 240 to 260. But the key thing is identifying what temperature it's switched off at, and then taking that temperature and reading off the values on your graph to give you the resistance here. So linking two graphs together. Question 2.7. Some chips were put into a deep fryer. In the deep fryer, water in the chips underwent a physical change and became steam. Why is this a physical change? So I should be thinking, right, physical changes, what do I know about it? Well, they're not permanent, they're reversible. So what actually made it a physical change? All water can change to steam. Well, that's true, but that what doesn't make it a physical change. No chemicals are involved when water changes to steam. Well, yeah, that is true. I mean, there's no other chemicals apart from the water, but that again is not what makes it a physical change. The change from water can be detected visually. Yes, it can be, but again, that's not what makes it a physical change. The water will recover its original properties if the steam is cooled. So it's about the states going from a solid liquid to a gas, but they can then reverse and making it a reversible state change, and their properties each time changes. Okay, so it can turn into a gas and then condense back to a liquid, and it would recover its original properties. Okay, so that would be 2.7. Okay, question 3 then. A trampoline is made from a sheet of material held by stretched springs. Figure 5 shows a child on a trampoline. You've got the child at position A and at position B. You can see at B the strings are being stretched. The question is, figure A, or position A, shows the child's maximum height above the trampoline. Position B shows the lowest position reached by the child when landing on the trampoline. Describe the changes of the energy stores of the child, the springs, and the surroundings as the child moves from A to B. You see you've got 4 marks here, but they've given you many more marks of the child compared to the springs and the surroundings. So therefore you can infer straight away 2 marks for talking about the child, 1 mark for talking about the springs, 1 mark for talking about the surroundings. So what I'm going to do is just annotate and do the answers around the diagram, but obviously you'd fill it into the correct space now. So for the child, we're looking at the changes in the energy stores. Well, what are they starting off at? They're in the air at the start, so they have gravitational potential energy. So in position A, the child has gravitational potential energy. Obviously make sure you write it out fully. And what is going to happen to it? Well, the child's going to be moving down, so therefore they are decreasing their GPE. They lose GPE, okay, or it's transferred to a different store. What is also happening is as the child then moves down, this GPE is being transferred into kinetic energy. The GPE is transferred to the kinetic energy store, so it is therefore increasing. But what happens when the child then hits the actual trampoline? Well, then they lose all of their kinetic energy, and therefore the kinetic energy would then turn to 0. Okay? The kinetic energy then decreases to 0. So you've actually got to say 3 things to get both marks here. You've got to say for position A, they are losing gravitational potential energy. They then gain the kinetic energy, but then when they hit the sheet of material, it decreases to 0. You'd get 1 mark if you're saying that they lose GPE, but you need both of these 2 points to get mark number 2. So that's about the child. The next 2 are only 1 markers. So the next one is about the springs. Well, what we can see is happening, the springs are getting stretched. So therefore, what's happening? Well, their elastic store is increasing. So I would keep that simple. the spring's elastic store increases, and then it says the surroundings. So as the child is then falling down, okay, what is happening to the energy store of the surroundings? Well, they are colliding as they are falling down. They will be colliding with loads of air particles. Now, air resistance is a form of friction. Friction generates heat, and heat is a type of thermal or a thermal store. So I would then say surroundings, as the child moves, they collide with air particles, okay, which increases the thermal store. Now it would be a very small, negligible amount, but that energy being transferred to the surroundings would still be happening. So that would give you your 4 marks there for the child, the springs and the surroundings. It then says, when the child is at position A, the trampoline is stretched by 0.056 metres. The elastic potential energy of the spring is 4.9 joules. When at position B, the elastic potential energy of the spring increases to 8.1 joules. Calculate the extension of the spring when the child is at position B. Use the physics equation sheet. So, you've been given loads of information here, and it's only really referenced elastic potential energy. So therefore your equation that you need is elastic potential energy equals 0.5 times by the spring constant times by extension squared. Okay? Now, you want to work out position B, but you've only been told one thing about position B, which is 8.1 joules. So we can't use this equation yet for position B. So therefore, we would have to work out what we're missing at position A. Now, we've been told at position A, we've got 4.9 joules of energy equals 0.5 times by our spring constant, which we haven't been told, and we've been told our extension is 0.056, okay, which must be squared. So what we can then do is actually figure out our spring constant of our spring. Rearrange the equation, 4.9 over 0.5 times by 0.056 squared equals our spring constant. Okay, now if you do that and type that into your calculator, obviously making sure that it's done correctly, you then end up with 3,125 Newton meters. Now that is our spring constant of our spring. Now it's the same spring between position A and B, so therefore we can now carry this number forward to position B. So you've been told at B you've got 8.1 joules. So 8.1 equals 0.5 times by 3,125, which we've just worked out, and then we're figuring out now the extension at B. Okay, now if I want to rearrange this equation, I would do 8.1 over 0.5 times by 3,125, which would give me my extension squared. I would then square root it, because I don't want extension squared, I just want the extension, square root it, and that would give me the extension. Now, if you've done all that, that should then give you 0.072 meters. So the extension at part B would be 0.072. So that is quite a difficult one, but it's just using one equation, and the trick is realising, right, put your equation down, work out what you can then figure out, and see where that can take you on to the next part. Even if you just got to this part here, you would still actually get 2 marks for getting to that stage, and then rearranging it would get you, and getting to B would get you the following 3 marks. But to show your working each time, substituting in what you've got. As the child bounces on the trampoline, the child does work. What is the work done by the child equal to? the average force applied by the child, the maximum force applied to the child, the total energy stored of the child, or the total energy transferred by the child. Now, this is basically just assessing what you understand by work done, and work done is energy transferred. It's the same thing. So if I'm doing a certain amount of work, I am transferring a certain amount of energy, and that's all this question is really getting you to recognise. Okay, question 4 then. A student investigated how the pressure of a gas changes on its temperature. The volume of the gas did not change. Figure 6 shows the equipment used. So you've got a pressure meter, you've got a mixture of ice and water that's being heated up, okay, and then the gas particles would travel down to the pressure meter, which would give you the reading. Pressure is sometimes measured in units called atmosphere. 1 atmosphere is 10 to the 5 pascals. What is 1 atmosphere in kilopascals? So if you've been told 1 atmosphere is 10 to the 5 pascals, I would personally just put that into a normal number. So 10 to the 5, okay, you move your point along, so 5 times, 1, 2, 3, 4, 5, so that is 100,000. So 1 atmosphere is 100,000 pascals. Now, we want the atmosphere in kilopascals. Kilo means 1,000. So 1 kilopascal, kPa, would equal to 1,000 atmospheres. But we've got 100,000. So all I would then do is take my number of atmospheres, or my number of pascals, and I would divide it by 1,000. Knock off 3 zeros, and that would leave me with 100. Okay, so kilopascals. So 100,000 pascals is the same as 100 kilopascals. That is 1 mark just in terms of unit conversions. Question 4.2. The student took the pressure readings for each experiment. Table 1 shows the pressure readings when the temperature was 50 degrees. Calculate the uncertainty in the mean pressure. Now, uncertainty is coming up a lot more in exam papers because teachers don't often go through uncertainty enough or regularly enough to make it really embed in students' minds. But this is how I would go about doing it. Uncertainty is basically the variation from the mean in the results. Now, they haven't given you a mean here, so the first thing I would do is calculate your mean. There's no anomalous results, so all I would be doing, add them up, divide by how many there are, which is 4, and that should give me a mean of 0.118. So your mean is 0.118, and that would get you 1 mark just by calculating a mean, which everyone doing a higher tier should do no problem. What you then want to do is work out your variation from the mean. Well, I can see my lowest value is 0.115, and my highest value is 0.121. Now, 0.0115 is minus 0.003 lower, and 0.121 is 0.003 higher, positive. So therefore my uncertainty, or my range from across my mean is 0.006, but I would just say my uncertainty is 0.118 plus or minus 0.003. So this part here, that is the most important part. Figure 7 shows a sketch graph of the results. The student said that as the temperature increases, the pressure increases. Give a better description of the relationship between temperature and pressure. So you can see you've got a graph here, and they've given it, it's right, temperature increases, pressure increases. But how can I describe a straight line on a graph? Now, a lot of people in the answer actually said directly proportional, but that is not right. Okay, if it was directly proportional, it would be going through the origin, and as one variable doubles, the other one doubles. That is not the case here. But what you can say is that it's a straight line, so therefore it's just a linear relationship. If you've got a straight line, it's linear. If you've got a curved line in any way, it's non-linear. Okay, question 4.4 then. So a pressure cooker is a sealed pot that uses steam to cook food. Figure 8 shows a pressure cooker. So you've got steam, water, a heater, and a platform for the food, and then a safety valve. When the water in the pressure cooker starts to boil, the amount of steam in the pressure water increases, and the temperature of the steam increases above 100 degrees. Explain why these changes make the pressure in the cooker increase. So this is getting you to explain why has the gas pressure increased when we start heating it up. Okay, and I've given you 2 bullet points, so make sure we refer to both of them. So what I would first say is more steam, I will write it on the lines, more steam means more particles in the cooker. And then I would say increasing the temperature means the particles have more energy and move faster. So as I'm heating it up, my particles, more energy and moving faster. So therefore, there are more particles which can collide with the walls of the container at a greater rate. So I've got more particles in the cooker, they're colliding and they're having a greater collisions more frequently. The greater rate slash more frequently. Okay, and then for linking it back, why is that increasing the pressure? Each collision gives more force on the walls of the container increasing the pressure. And that would be your 5 marks here. 1 mark for saying that there would just be more particles, 1 mark for saying that they'll be moving faster, 1 mark for saying that they'll be colliding more at a greater rate or more frequently, and then recognising the fact that the particles, as they collide, exert a force on the container. Right, question 4.5 then. If the pressure in the cooker becomes greater than 200, then some of the steam is released through the safety valve. The released steam expands as it moves into the atmosphere. Explain how a change in the density of the steam is caused by a change in the arrangement of particles as in the steam as it is released. So if you've got high pressured steam all in here and then it comes out the safety valve, what is then going to happen to it? Well, it's going to start spreading out, okay? Because the particles then can spread out quickly, like steam coming out of a kettle, spreads out. So I would start off just by simply saying the particles start to spread out. Why are they able to do this? Because they're now in a bigger volume. Okay, and then is linking it back to the question, how does that affect the density? This decreases the density And you can link it back to the equation because density is equal to mass over volume. And those would be your 3 marks there. Question number 5 then. A camera in a mobile phone uses an LED to provide light when taking a photograph. The student investigated how the potential difference across an LED varies with the current in it, and figure 9 shows the circuit used. So this is your circuit you should recognise from your voltage current graph required practical, ammeter in series, voltmeter in parallel across the component that you're testing. The student closed the switch and the voltmeter gave a reading of 5 volts. The ammeter gave a reading of 0 milliamps. The LED did not emit any light. Explain how the student could have changed the circuit to make the LED emit light. So you've got to be thinking, right, I've got voltage, so there's nothing wrong with my cell or battery, that's working, but I'm not getting any current around my circuit. What might be causing the current to not be going around my circuit? Well, the fixed resistor would be reducing it, yeah, but that's a fixed resistor, nothing we can really do or change about that. What we can change though is our LED itself, because remember, even though it's an LED, it's still a light emitting diode. The job of a diode is to reduce or effectively act like a roadblock, has a really high resistance in the reverse direction. So if I want to then allow my current to flow through my diode, I flip it round. Okay, so if I turn my diode the other way round, this roadblock then isn't there, and the current will then be able to pass straight through it. Because remember, diodes is where their voltage current graph looks a bit like this. It goes flat and then shoots up. It's got a high resistance in one direction, but it has a low resistance in the other direction. So what should the students do to make the LED emit light? Switch the direction off the diode as it has a high resistance in the reverse direction. Okay, and that's it. Question 5.2. The student changed the circuit so the LED emitted light. The current in the circuit was 290 milliamps. The power of the LED was 0.98 watts. Calculate the potential difference across the LED. Use the physics equation sheet and give your answer to 2 significant figures. So I've been given current, I've been given power, and I've been given potential difference. Okay, so I look at my equation sheet that's got those 3 things in it, and I can see it's the equation power equals current times potential difference, okay, or PIV. My current in my circuit is 290 milliamps. Now what that should be jumping out at you straight away, 290, we don't use milliamps in equations, we use amps. There's 1,000 milliamps in an amp, so 290 divided by 1,000 gives me 0.29 amps. So my current should be 0.29. My power is 0.98. I want to calculate my potential difference. So I can rearrange the equation. Potential difference is power over current. Power is 0.98, current is 0.29. If you do that, that gives you an answer of 3.379 volts. But I wanted to 2 significant figures, so draw your line, and then it should, you round it up because it's a 7, so it should just be 3.4. Okay, so a lot of the time I might expect a 5 marker to be using 2 equations. 5 or 6 marks for 2 equations, but this one just has the unit conversion in for that extra mark. Okay, so that's 5.2. A traditional camera uses a flash unit to provide light. Figure 10 shows a flash unit on a traditional camera. The flash unit emits light from xenon gas in a fluorescent tube. What happens when the xenon atom emits light? Electrons in the atom fall to a lower energy level. Electrons in the atom move to a higher energy level. Electrons leave the atom, causing radiation, and electrons transfer to the atom from the electrical circuit. This one is actually quite a hard question. Not many teachers would have gone through this in detail, to be honest. But just remember, when it's talking about energy levels, it's just talking about electron shells. Now, if you're giving off light, if I've got electrons, okay, in an outer shell, if they fall down in terms of energy to a lower energy shell, then that would emit light. It's just one little random fact. It comes up a lot more about A level, but yeah, electrons can move between energy levels or energy shells. If they fall down towards the nucleus, it actually gives off energy in the form of light. I wouldn't worry too much about it. That's just 1 mark there. Question 5.4. When the flash unit is used, there is a mean potential difference of 200 volts across the fluorescent tube. The flash of light lasts for 2.8 times 10 to the negative 4 seconds. 1.4 joules of energy is transferred. Calculate the mean current. Use the physics equation sheet. So you've got your equation sheet and you've been given potential difference, you've been given time and energy, and you want to find the current. Okay, so again, if there's a 6 marker, so that pretty much is telling you you're going to need 2 equations. And then you can think about, right, what equations can I use? What have I actually got that can help me now? Well, what equation has 2 of these things in? There's nothing really in terms of electricity that goes with time at the moment, but I've got potential difference and I've got energy. What equation have I got that links those together? Well, energy equals charge times by potential difference. So that can be the first thing that I can do. I've got my energy, so energy equals charge times by potential difference. My energy is 1.4 joules. My charge, well, that's unknown. My potential difference is 200. So I can just get my charge as being 1.4 over 200, and that gives me 0.0070 coulombs of charge. I then can think about, right, I've now got a charge value and I've got time here. Well, I know charge. If I know charge, which is Q, and I want to know my current, and then I've got time as well, well, then I can use this equation to find my current. So what I would then do, charge equals current times time. I know my charge from my previous answer, 0.0070 equals current, which is what I actually want to find out, times by my time, which is 2.8 times 10 to the negative 4, making sure I put that in my calculator correctly. Rearrange it. To find current, it would be charge over time, 0.0070 divided by 2.8 times 10 to the negative 4. Do that on your calculator, and that would give me a current of 25 amps. And that, 6 marks there for using 2 equations. Can be quite difficult, but remember, if I give you the equation sheet, just look, what equations can I use? What can be the next thing that can help me on the journey of finding the final answer? So that's the end of question 5. Okay, so question 6 then, which is the last question on this paper. A smoke detector contains a source of alpha radiation in a plastic case. A source of beta radiation in a smoke detector would be more hazardous than a source of alpha radiation. Explain why. So most smoke detectors would use an alpha source of radiation. Why do we use that? Well, it's because alpha is not very penetrating. Alpha, the biggest of your radiations, can't get through any materials, stopped by paper, stopped by skin. So alpha, it's stopped, we know that, but now they're saying, why would beta be more dangerous? Well, beta is more penetrative, or has a higher penetration, that could escape the plastic case. Okay, so that's why, but then how is it actually more hazardous? Beta particles could then irradiate, which just means expose, okay, irradiate or pass through skin of people walking past. So I've said why it is more dangerous, and then how it could actually affect the hazardous nature, okay, to people. It then says actinium is one source of alpha radiation. An actinium nucleus emits an alpha particle and turns into a francium nucleus. Determine the values for A and Z. Now, an alpha particle, we should remember, has a mass of 4 and 2 protons. So it's 2 protons and 2 neutrons, which is the nucleus of a helium atom. So if I'm giving off an alpha particle, my actinium has lost a mass of 4. So if I'm losing a mass of 4 to go back to what it was, I would add 4. Okay, so that would be 227. And then because I've lost 2 protons on this one, I would add 2, and that would put me back on 89. Okay, so it would be 227 and 89. A lot of teachers then obviously teach it the other way, that you start off with your radioactive atom, okay, it would decrease by 2 protons because it's lost 2 protons, but it's lost a mass of 4, okay, and that would go to that equation there. Question 6.3. A teacher wanted to find out what nuclear radiation is emitted from a source. A teacher placed different barriers between the source and the detector. The student recorded the count for 30 seconds after each barrier was put in place, and table 2 shows the results. So you've got a barrier, none, which has your starting reading, paper, aluminium, and then lead. Explain what nuclear radiation was emitted by the source. So nuclear radiation, remember, is just basically just saying, is it alpha, beta, or gamma? Okay, you just need to say what is the results showing and explain why. So you can see here, as it goes from no barrier to having paper in the way, the rate has decreased quite a lot. Okay, so therefore I can know straight away that alpha can't get through paper, so the paper is blocking alpha. There is a decrease in radiation as alpha is blocked by the paper. Okay, so I've clearly said that alpha is being some radiation is being stopped by the paper, and that it is alpha. However, some radiation passes through the paper okay, still 149 parts of radiation are getting through the paper. So therefore, another type of radiation must be there. Okay, so what can then pass through paper, but then it can't pass through any aluminium or lead? Well, that would then be beta. So however, some radiation passes through the paper, which must be beta, because beta cannot pass through aluminium, which has a 0 reading. Because if it was gamma, then there would still be a number here, maybe about, well, I don't know, about 100-ish. If it was gamma, because the gamma would have been able to pass through the aluminium, but the aluminium is blocking all the other radiation, so therefore it must be beta. So your answer here is showing that you've got some alpha because it's being blocked by the paper, and you've got some aluminium because it's gone to 0. Last question on the paper then. Figure 11 shows how the activity of 4 different radioactive isotopes, A, B, C and D, change over time. So you've got the time in years and the activity in becquerels. Now this is, you should recognise it as being a half-life graph. But instead of having 1 substance on it, you've got 4. The question says, write the isotopes A, B, C and D in order of their increasing stability of their nuclei. So basically going from the least stable to the most stable, and then explain why you've put that order. So if you've got a half-life graph, you need to work out which one's giving out the most amount of radiation in a certain length of time, which is the half-life, or the time it takes for half the radioactive substance to decay. If it's got a really short half-life, then that is more unstable. If it's got a longer half-life, then that means it would be more stable. So remember, short half-life, unstable. Long half-life means it's generally more stable. So you can work out the half-life for each of these substances. So A starts at 400, so I would go to 200 and then down and see its half-life in years. And then I would go for B, starts at 250, so I'd go to 125 to the line of B. Okay, so I can see straight away that B has a shorter half-life than A, so B is more stable than A. Now if I try and do it on C, you see actually, it starts at 100, so you go to 50, but C never crosses 50. You'd have to extend the line going and going. Probably can't even fit on this graph. So we're not going to draw that line on. But D starts at 150, so I'd go to 75 and down, and you can see that that one is more stable. So in terms of order of stability, I've got line D, then B, then A, and then somewhere down here would be C. So that gives my order, D, B, A, C, in terms of ordering their half-life. D, B, A, C. And why is this? Explaining it, because, as I said, a longer half-life is more stable, or elements with a longer half-life are more stable. Okay, so the answer, or the order, is in order of increasing half-life. Okay, and that's how you would get to the answer here. Not many people actually got 3 marks on this. It's quite a hard question, but the trick is recognising, oh, I've seen this type of graph before, it's just talking about half-life. Okay, so that's the end of this paper then. Hopefully it's been useful, and as I said, the paper and the mark scheme are linked in the description. Okay, thank you.